Set timer for 50 minutes. Hi guys, we're going to talk about section 22.4, magnetic field strength, and I'm only going to record this bit, and hopefully after these 50 minutes are over, we won't need to do much more as far as videos go, but we'll see. So here's the whole thing. We've got a magnetic field. You can see it here in blue. And ways to measure different field strengths. When we were dealing with the electric field, what did we do? We had Coulomb's law, right? And then that gave us F equals QE, right? Well, we want to do a similar thing and figure out the force on a moving charge in a magnetic field. And of course, charge means that it's an ion or it's something where there's an excess charge on it, right? So let's say we've built a uniform magnetic field. The last thing we ended up with today in class was a solenoid, a coil, a wire coil that has a current running through it, and that generates a B field, okay, a nice good magnetic field. Uniform, that's one of the keys. We want it to be a uniform B field. So we've done that. Well, however we've done it, we don't know, but we've created this uniform magnetic field here in the figure, and we have a charge, Q. This little charge Q moving with some velocity V perpendicular to the B field so that the theta angle is 90 degrees. So we want to know what the magnitude of this force is, all right? That's our thing. So we've got this equation, the Lorentz force equation, okay? Another person's name, Lorentz. They have given us this equation, and so we're going to use it. We're going to get a force, so the units on this whole thing is going to be newtons in the end. We get a force equals to the actual charge times the velocity times the B field magnitude of the B field, times the sine of the angle between them, between the velocity and the B field, okay? So that all kind of makes sense. It's pretty simple. Let's leave it like that. That's it. I mean, that's the equation. Let me get rid of these guys. And let's just box this thing in because it's super important. Okay, it's a big equation for us. Now, we've got the magnitude of that force, but what is the direction? Okay, what is the direction that the force is pointing? So here's how we do it. Of course, we use the right-hand rule. So we're going to have to use the right-hand rule. And we're going to take that rule by placing our fingers along B. I have to read. There's a lot of different ways to do this. Some people put their fingers along V, curl towards B, and then your thumb points in the direction of F. Okay, so F is out of the page. Okay, that's the direction for F, out of the page. So what I have here is, I think what they have in the book. So you place your fingers along B, your thumb along V, and then your palm points in the direction of F. Or if you were to curl your fingers, you would notice that your fingers curled upward and therefore out of the page, and therefore you still get this. Okay, so I don't know. I kind of like my version. So here's my version. Place your fingers along V so they can curl toward B. Okay? So if B was pointing down, you'd want to have your V, your fingers, you'd kind of have your fingers in a way where you could curl them toward B. But B is going up, so you put your fingers so they can curl towards B upward. So one way or the other, you place your fingers along V, and then they curl toward B. At that point, your thumb points in the direction of F. Okay? So, place your fingers along V, curl them toward B, and then your thumb points in F direction. So, that's it. The right hand rule comes to our rescue again. Either way, you can do it like the book does it. You can do it all kinds of different ways, but that works for you. So let's use our equation. This equation, let's call it equation 1. Let's use the Lorentz force equation and solve it for B. So I'm just gonna, yeah. Okay, everybody okay with that? Good. So now we can figure out, if we know the force and all the angle and the velocity and the charge, we can figure out what our B field is. Okay, so if we were to look at this in units, we would notice that newtons on top, we've got charge in coulombs on the bottom, we've got meters per second on the bottom, and so those are our units. That happens to equal 1 Newton, and we're dividing that 1 Newton by, now here I'm going to do a little exchange. I'm going to turn coulombs per second times a meter. So we end up with 1 Newton over 1 amp times 1 meter. Okay, so that is the units for a B field, but that's ugly, right? Nobody likes that. So what we say then is that that equals 1 Tesla. Okay, a Tesla. So we are honoring Nikolai Tesla. Almost said Tesla. Nikolai Tesla, and we call it a T, all right? So we've turned newtons into an N. We're going to take a Tesla and make it a T. So our B field units are Teslas, and that is the SI unit. So you want to use Tesla if you're going to end up having to solve equations, and that'll always get you back to your meters, your coulombs, and your seconds, okay? And your newtons. So it stays SI at that point. All right. Okay, so one of the other units that gets used is a Gauss. All right. It's another unit that can be used. Let's do. Okay, so there's a Gauss. So if you were to take a Tesla and multiply it by 10 to the minus 4 times a Tesla, you'd get a Gauss, okay? And you probably don't know, G equals Gauss. And it's just less, okay? So on the surface of Earth, we've got a B field, so B of Earth is equal to about 5 times 10 to the minus 5 Tesla. And if you were to write that in terms of a Gauss, that is 0.5 Gauss. Okay. So what we've seen so far is all about the forces and the units and how do we come up with a force for a moving charge. Can you have a force when the charge is not moving? Can you have a force? No, you can't. There's forces on things, true, but you don't get a magnetic force, okay? We want to know what that magnetic force is. We have to have a velocity for the charge through the B field, okay, through the magnetic field. Okay, so let's do an example. Should I leave any of this? No. I can leave that. All right. So let's do an example. So we've got a charged glass rod. It's charged. Charged glass. Let's do this, and then we'll call this an example. A charged glass rod with 20 nanocoulombs on it. Okay, we're going to throw it east. Okay, so thrown east with velocity equal 10 meters per second. And what we want to know is, in Earth's magnetic field, what is the force? All right, so what is the force on that rod in Earth's magnetic field? Oh boy. So, good. Let's solve this problem. First of all, you got to know which way the magnetic field is for the Earth. So, I don't know if you guys remember this or not, but if your compass is pointing upward to the north, then that means your B field is pointing upward. Okay? So let's draw it out. Let's put a little B field here. Here's our B field. And we're going to say that this is east and this is north. All right? And we've got a glass rod that we are throwing in this direction with a certain V. And we already know that it's directly east, so our theta, we can just write down theta is equal to 90 degrees. Just real quick, let's do the sine of theta. Theta 90 degrees, it's going to be the sine of 90 degrees is 1. Hopefully you guys remember that. And now we can write down our forces. Our force equation. Our force equation is F equals QVB sine theta. All right, QVB sine theta. Well, that really is just QVB in our case because the sine of theta is 1, so we don't need to worry about that. And we can just plug in numbers. So we've got 20 times 10 to the minus 9. We're going to multiply that by 10. We're going to multiply that by our B field. And the Earth's B field in Teslas, I think we should use Teslas. Let's stay with SI units, is 5 times 10 to the minus 5. And what I'm not going to put the units for each of these things here. What I'm going to do is I'm going to say, well, all in all, that has to be newtons. Okay? I always want you guys to go through and look at the units, make sure everything's working out correctly. But in this case, we already know pretty much that we've done this correctly. So we're going to have newtons. So our force is equal to 20 times 10 times 5, and then 10 to the minus 14. That ends up being 10 to the minus 11 newtons. Now, which way is this happening, right? Which way is that force going? So we're going to take our fingers, we're going to put them on B around V. We're going to curl them towards B, and our thumb is going to point straight up. So, out of the page. So we can put a little vector sign on here, and we can put our direction, and we could say in that direction. And that is our vector in this situation. All right, so you throw a rod that direction, it's going to have this small little force on it, and wanting to lift it up, wanting to throw it up into the air. Okay, so that's a good example. Nice, solid example. What about, what's the equivalent mass of the object was held up by that magnetic force in the air? So, what do I mean by that? Okay, so, let's say we do this. We do this whole thing. Oh boy. What mass will allow the rod to hang in the air? Because we've got this force right here lifting us above the ground. Okay, that is the direction of the force. It's lifting us above the ground, right? So if we were looking at this scene, we're looking at that scene from space, basically from up above, right? And the force is coming at us, so that means it's lifting up out of above the ground. So what is the mass that will allow this rod to hang in the air while it's flying left and right? Okay, so let's draw a free body diagram. Here's our force of our magnetic field. Here's the force of gravity. And we are going to do a thing where we want them to be equal. So our force of the magnetic field is going to equal our mg. And if we want to know what the mass is that works out to be, then we're going to solve it. FB over G. Good. So we've got 10 to the minus 11 over 9.8, and all that's going to be in kilograms. So this is the mass. This is the mass that we're going to get. It can't be that much, right? We all know it has to be pretty light. And if you were to plug the numbers in, you should get about 1.02. I said 2 and wrote 8, because I was thinking 100 minus 98. Oh, God. It's a 2 times 10 to the minus 12. And that's kilograms. If you want to think of it in grams, that is equal to 1.02 times 10 to the minus 9 grams. And we could just say that it's roughly 1 nanogram. I don't know if you know how small 1 nanogram is, but that's my equal sign. Let's redo it. My approximately equal sign. So the mass is about 1 nanogram. Pretty small. Okay. If you want to compare what a real glass rod weight is to this, we can do it. The mass of a glass rod is roughly 50 grams. I'm going to put it all in kilograms. Let's work with kilograms. So 50 would be 0.5 kilograms. So the mass of a glass rod is around 0.05 kilograms. And we could then take the mass of our object and divide it by the mass of a glass rod and get the difference. Our object is let's just say 10 to the minus 12. Let's forget about the 0.02. And we're going to divide that by 0.05. And we're left with 20 times 10 to the minus 12. It's just so much smaller. It's about 50 billion times smaller. So the glass rod wouldn't be, you just wouldn't see any lift to the glass rod. But if you had a 50 billion times smaller glass rod with the same amount of charge, you could throw it and it would hang in the air like a curveball in baseball. Okay. So, good. All right, we're going to move now to the next section. So we're going to move to, I hate when I do that, section 22.5. This is particle physics. And cosmic rays. It's cosmic, brother. It's cosmic, baby. All right, cosmic rays. Let's say we have a uniform magnetic field. All right, who knows how we did it? We produced it. We're good like that. And it's going to point down. Okay, we're going to have it shoot down into our lab table. Okay, so here I'm going to draw up. I don't want to do it like that. I want to do it like this. Okay, so imagine this region is our into the page magnetic field. And we've got some particle is going to come screaming on in here. With some velocity v. Okay, so it comes moving into our B field with some velocity v. Now, let's see. Am I... does it matter yet? I'll change the sign if I need to. There are figures that you might want to look at. 22.19 is a cloud chamber, which is a very early particle detector. And we learned a lot about particles from cloud chambers. And then 2220, that's a force diagram. Okay, so we've got this velocity going in. Let's first, before we do anything, we want to note so we've got some charge Q. I don't know if it's positive or negative yet. We'll see in a minute. We've got this force Q, but we're going to go along V We're going to curl toward, yep, it's a negative. It's a negative particle. We're going to curve toward B, and our thumb is going to point in the direction of the force. However, F equals QVB. The sine of theta is going to be 90 degrees. Sine of theta is 1. So because the B field's pointing straight down and our V is in this plane. So QVB. Now, the only thing is if the Q is negative, our force is going to point in the different direction. It's going to point in the opposite direction that we get. So instead of the force pointing this way, which would be positive, the Q is negative. So the force is actually pointing in that direction. Okay? So let's erase this one. We'll leave that one. And we've got some momentum going. So it's kind of screaming in here. And then it does something like this. And eventually it ends up going in a circle of radius r. All right, and our force, what do you know, is our force of the magnetic field, and it is equal to our centripetal force because it's holding it in. So we've got, I'm going to get rid of the negative sign because I've already flipped the sign of the force, so I can get rid of both this and this. And I can say then that our mass, the mass of our object times AC, you guys should remember AC is mr omega squared. That's our force. That's going to equal our QVB. So very convenient. Mr omega squared equals our QVB. So good. Now, I'm just going to write MAC. And hopefully you guys remember that AC is equal to R omega squared. All right. So let's say we want to know, what do we want to know? We want to know what the radius of this circle is. Okay? So what is R for the circle? What is R for the circle? Well, we're going to take this equation and solve it for R. So mr omega squared equals QVB. That's going to give us R equal to QVB over our mass times omega squared. All right, fine. But now we have to do something. We know that there's a relationship between V and omega squared, right? So what is that relationship? V equals R omega. So if we want all of this in terms of our velocity that we have going in, because that's something that we're given. So we're going to say that means that omega is equal to V over R. And if we have omega squared, we've got V over R squared. So let's do that. And we're going to substitute in omega squared. So R. Why isn't this working? Why isn't that working? I don't like this. I don't like it. I don't like it. Let's keep it simpler. This is going to be too much rigmarole. This is too much. What is AC in terms of velocity? Well, that's v squared over r. This should get us to the same place, of course, but I'm going to do it with v squared over r instead of r omega squared. So let's do it with v squared over r. We've already got v squared in there. I think it's the right way to go. So m times v squared over r. Yeah, this is better. Okay, now let's solve this for r. So we're going to take this r and we're going to move it up to that side. We're going to take all these things and we're going to move them down underneath the v squared. So we've got mv squared over qvb. We can get rid of this v, we can get rid of that squared, and that means that we've got mv over qb. This is much simpler to see. The other way doable, yet gives you the same answer. But this is a good takeaway because what happens is somebody will give you the B field, somebody will give you the charge of the object and the mass of the object and some velocity of it entering into the B field. They'll ask you what is the radius of curvature for the circle that it develops. Okay, so that's how you would do that. However, you could be given all kinds of stuff, right? You could be given the radius and the velocity and asked for the B field, or however somebody wants to do it. Okay, so far so good. Let's do another example. I think this one is out of the book. This is example 22.2. And we've got a bar, an electric bar. Not electric. We've got a bar magnet. So there's a north end and a south end. We've got a B field going on. And we've got an electron coming in. What is the size of our B field? B field is equal to 0.5 Teslas, which, by the way, I just want to let you guys know that a Tesla is very large for a magnetic field. So 0.5 of a Tesla is a huge magnetic field. You would be very hard pressed to get a magnet that would do that field. Let's say we've got electrons coming in. Okay, we've got an electron coming in, and it's doing 6 times 10 to the 7 meters per second. So it's screaming on in there pretty fast. Maybe it's a neodymium magnet. I don't know. But what do we want to know? We want to know the radius r. Now, here's the thing. What is the radius r? What really is going to happen is this guy, this electron, is going to coming on in there, and it's going to go like this and get wrapped up in this field. And the radius that I'm talking about is the radius of curvature as it wraps itself around that field. So imagine that it's going like this in a helical coil, and we want to know this radius. I could have drawn that bigger, but essentially these are the same coiled fields. Okay, so that's what's going to happen. It's going to come in, it's going to get wrapped around that. What is the radius? So we do our thing. We use R is equal to the mass of the electron times the velocity of the electron divided by the charge of the electron and times the B field. What's that going to be in? It's going to be in meters. So let's just stick some units on there. Meters. Mass of the electron. Oh boy. 9.11 times 10 to the minus what? Yeah, 31 kilograms. We know what our velocity is. We're going to multiply that by 6 times 10 to the 7 meters per second. I don't know why I'm putting units, because it's going to be all meters at the end anyway, but we're going to divide by our charge. And everybody knows it's 1.6 times 10 to the minus 19 coulombs. And we're going to multiply that by our B field, 0.5 Teslas. I know it's a mess, right? If you want to go through, make sure all the units work out so that you have meters. Fine, it's a good move. This ends up being 6.83 times 10 to the minus 4 meters. Then there's a few ways you could write that. You could write that as 0.683 millimeters or 683 micrometers. So there's a lot of ways to write it. This way is just as good as any. Okay. Figure, let's see. Look at figure 22.22, and they have a good diagram, okay, of what we just saw. So that would be a good diagram. Just so you guys have a clue a little bit about my history, figure 22.25 is Fermilab, and I worked there for about 2 years. So anyway, and also the size of a magnetic field. Let's deal with what you might see as the size of a magnetic field. So the largest magnetic fields out there so there are these things called fusion reactors. All right. So a fusion reactor all right, we've got 5 minutes. A fusion reactor is great. They do this thing where they try and hold in a torus it's hard to draw a torus. Imagine a donut. I'm trying to draw a donut. Okay, so here's our donut. And they have to have B fields that wrap around this thing and keep the material running through the middle of the donut. Okay, it's called a toroid. And there's B fields that hold the charged particles in there. Those B fields have a magnitude of up to, so I've heard some people say 20 Teslas, but 13 Teslas I think is about the largest. They've probably done 20, but whatever. So a B field of 13 Teslas, and that's just huge, okay? Huge. So most of the time we're going to be dealing with 10 to the minus 5 Teslas, or 10 to the minus 3 to 10 to the minus 5, maybe 10 to the minus 8 Teslas. Okay, so that's kind of the range in which we'll be working. 13 Teslas, wow, that's huge. Okay, so okay, I'm going to record another one so that we get all the way through chapter 12. So that's going to require another video, but no fear, have no fear. I'm here, I'm ready to do this. So that's it. We're going to come back and we're going to look at section 22.9, 22.10, and then we're going to dip back to 22.6, 7, and 8.